Right, when we last met, I said that I was going to show you how to find the moment about individual axes. Okay, so here's the basic rules. If a force passes through the axis, so this is my x-axis, if a force passes through the axis, then there's no moment caused by that force. If a force is parallel to that axis, there's no moment caused by that force. You will have a couple any couple moments on your free body diagram wrapped around that axis. So I do have one moment. I have this reaction moment about the x-axis is wrapped around this x-axis here. But then notice that I have a force here that passes through the x-axis. I have a force here that passes through the x-axis. Neither of those, basically their perpendicular distance, if you will, is zero. Any force that passes through these points, they cause zero moments, right? And then again, any force that is in the direction of that axis, in this case the x-axis, this x direction force, it will cause no moment. Again, this is basically saying the angle between these two, remember, the cross product is the two magnitudes times sine theta, and the angle between this axis and this x direction force, the angle between them is zero. So sine of zero is zero. So there's going to be all three of these forces, none of them actually cause a moment about this x-axis. So the reaction moment in the x direction is not required. It ends up being zero. There's no actual reaction moment required about the x-axis because there's no forces. Another way to possibly do that, if I pull out a separate sheet of paper, if I look at basically the y-z plane, and the x-axis is coming into and out. You can't see that, I apologize. But look at the y-z plane, and basically the x-axis is coming into and out of the page here, right? And what I've got then is I've got this 12 newtons coming down essentially in the y direction, 12 newtons, and I've got 30 newtons going down here. And you say, okay, well, what is the moment about this point? This point basically is my x-axis. It's the origin, but it's also, I'm looking down the x-axis, and notice there's no moment because both of these pass through that point. So there's no moment caused by them. And again, the 9 newtons here is in the x direction, so it doesn't cause a moment about that x-axis. So it's another way to kind of think about it mathematically, is shrink this down to a two-dimensional view looking down the x-axis, and sometimes that'll help you write this equation. Let's do a couple more, see if that helps. I know that's really abstract. I know a lot of people kind of struggle with it. You are more than welcome to go this route, where you write one big long vector equation, and then you pull out all of the I terms. There's going to be some I terms show up in these R cross Fs. You add this to it and set them all equal to 0. You're welcome to write this as one big long vector equation and solve out, separate out all the I's, all the J's, and all the K's into 3 different equations and then solve them. That's fine. I'm showing you kind of a way to skip that step if you want. So let's look about some moments about the y-axis, some moments in the y direction. This is my y-axis. Okay, so I do have this reaction moment applied about the y-axis because this thing cannot actually rotate about the y-axis at this point. So there's a reaction moment in the y. I need to add that just like any other couple moment in my equation. Now in this y-axis here, I look at forces that pass through this y-axis. Well, this 9 newtons does pass through that its line of action does pass through that y-axis. So there's no moment caused by any force that passes through that. Its line of action passes through that y-axis. That means its perpendicular distance is 0 essentially. This is in the y direction. So any force in the y direction does not cause a moment about the y-axis. But I've got this force here. There's 30 newtons out here. I got 30 newtons out there. It is 5 meters perpendicular from that y-axis. In the x direction, it's 5 meters out. And if you look at the direction of that, so if I put my thumb in the positive, can't quite do it. If I put my thumb in that positive y direction, notice that this force, this 30 Newton force, is basically pushing down right there. Right? So notice that is causing a counterclockwise rotation when viewed from that y-axis, so to speak. Right? So that is then causing a moment, a positive moment. Because again, thumb out here, that force is pushing, can't see. Thumb out here, that force is pushing 30 newtons down in the positive y direction. 30 newtons, and it is a distance of 5 meters from that y-axis. And that's the only way. So I've got 3 forces here. All 3 of these reaction forces pass through this y-axis. It was the same thing with the x-axis. I didn't mention those earlier. I've got this x-axis. All 3 of these reaction forces pass through or in the direction of that x-axis. So none of them are causing moments either. But I do have this one force, 30 newtons, 5 meters away from that y-axis, causing a positive y-direction moment. So this is one equation, one unknown. I can solve for this. And then finally, sum of moments about the z-axis. Set that equal to 0. Again, I've got a reaction moment in the z-axis up here. I need to add all couple moments into the equation. Add or subtract, whichever direction they're rotating. I've drawn this in the positive, so I'm just going to add it. And then again, we look at our diagram here. Okay, this 30 newtons is in the z direction. No moment caused there. This 12 newtons, this is going to cause a moment. So if I put my thumb in the positive z direction here, and if I look at what this 12 newtons is doing, it's going like this. So it's trying to open my hand. Notice that it's trying to open my hand. That means it's actually in the negative z direction. So if I put my thumb in the negative z direction, that 12 newtons is trying to close my hand when I put my thumb in the negative z direction. So it is. And remember, if you're like me and you're left-handed, you can do that. If you're right-handed, you have to actually set your writing utensil down and use your right hand to figure out the direction of the moment caused. So I've got minus 12 newtons. It's causing a negative moment about the z-axis. And its distance is 5 meters from this z-axis. And then also I've got this guy. So if I put my thumb kind of in the positive z direction, and I take this 9 Newton force right here, and I push my fingers in the direction of that 9 Newton force, notice they're causing my right hand, to close there. That is a positive 9 newtons. And it is acting, so positive 9 newtons, and its lever arm, or moment arm, notice its line of action is 3 meters from the z-axis. I gotta pause. I'll be right back. All right, sorry, I had a call I had to take real quick there, but it gave me a chance to maybe draw something. I know this is a bit abstract. It gave me a chance to maybe draw this in a two-dimensional format. So again, if we look at this, and what I've done here is I've taken this arm here, and I've drawn it just in the XY plane, right? So I've drawn, again, just the XY plane, and let's rotate it around so we flatten the Z-axis. We just look at the XY plane of this thing, right? And if we do that, then maybe this helps. Maybe this makes it a little bit easier. If you look at, what are your sum of moments about point Z in this case? Well, you've got now, and again, I've got this reaction moment about the z-axis is being applied. So sum of moments in the z, this is MRZ. Again, if I'm taking a two-dimensional look at this thing, this is causing a counterclockwise rotation. So that's plus 9 newtons at a distance of 3 meters. Right? And then this is minus, then, because this is causing a clockwise rotation, this is 12 newtons. This is minus 12 newtons acting at a distance of 5 meters. which I think is what we've got right here. Yep, sure enough. I was hoping I did that right. But so if that helps, draw a version of it in 2 dimensions. What does this thing look like if I look straight down the z-axis? What does this thing look like if I look straight down the z-axis? Just draw the xy plane the way I'm used to seeing it. Draw a negative x force, a negative y force out here at 5, 3 in the positive x and y directions. And then just see if that helps. If you understand how to compute moments in 2 dimensions, this is basically computing moments in 2 dimensions, like everything we do in 2 dimensions, but it's applying it on a 3-dimensional scale. Notice I've got 3 equations, 3 unknowns here. I've got 3 more equations, a total of 6 unknowns. I've got a total of 6 equations, 6 unknowns. That's solvable. I'm going to pause this here and do a couple of things. I'll be right back. Number 1, I'm going to compute answers, but number 2, I'm going to do something else. Okay, I was hoping you paused there, and as I paused and actually calculated the numbers. If not, it's not like these are difficult equations to solve. These are the answers, right? So double check that. Make sure you understand kind of however you want to go about doing it. Again, I've shown you here how to go about trying to find the moment about each axis. Now, I did say earlier you could write a single vector equation, which as I had us paused here, I took a moment and went ahead and took the liberty of doing, and I'll walk you through that. Again, what you need to do, I've got 2 forces here, so each force has got its own position vector. So I've got 2 forces acting on this thing. I've got force 1 acting, so this is force 1 minus 9 minus 12, minus 9i minus 12j newtons. And it's acting out here. I just wrote a position vector out to its line of action. That's just simply the point where that force, I'm calling this point 1, and I'm calling this point 2 where this other force is acting. So this is point 1, position vector from here to here, 5i plus 3j meters. And this is force 2, that was the minus 30 newtons. It's out at 5i meters, minus 30 newtons out here at 5 in the I direction. And again, what I'm doing here is I need to write a vector equation where I'm adding up all the r cross f's as vectors and add it to all the couple moments that are applied. Well, in this case, the only couple moments are my reaction moments. So add in all the couple moments and the I, j, and k directions. Do all the r cross f's. So the sum of all the r cross f's, I've got 2 r's and 2 f's, so I cross each of those together. So do your matrices here. So r1 cross with f1 here. R2 cross with F2 here. Got to get your signs right. I messed up the signs the first time. I'm like, wait, why aren't the signs working out? The signs actually work out. These 2 matrices simplified down to this quantity here. And you could write J before K here. I've written K before J. And then you plug that back into this original work here. Again, I'm writing one big vector equation. Total moments all the way everywhere are all the R's crossed with all the F's. Add all the couple moments. So substitute in here where I've crossed all the r's with all the f's, and this is what it simplifies. This is r cross f, the sum of r cross f's. This is what it simplifies down to. Add to it all the couple moments, right? And then do what we call equating coefficients. So equate all of the i's together. Everything that's multiplied by the I vector, equate that together, and that becomes my sum of moments in the x direction. So the only thing I've got in the I direction is this mrx, and that's 0, which is what we found earlier. Because it's the only thing in the x direction is that reaction moment. So it's not needed, it becomes 0. In the y direction, the j, equate all the j's. So everything with a j multiplied to it, add those all together. Some moments in the y direction, those had to be 0. So everything with a j term gets added in this equation. So this moment here, and I've got a j term here. Set that equal to 0 and solve. And the same thing here for the z direction. Everything that's got a k in it, I've got this reaction moment here. And I've got this k term that's minus 33 here, minus 33 Newton meters there. Set that equal to 0, solve, and you get the same solutions we had earlier. I don't care which way you do this. Do which way you're comfortable with. If you're comfortable with writing one big long vector equation and equating coefficients out into 3 separate equations, if you can kind of look at it, think about looking at the the zy plane and look at the forces causing a moment about the x-axis and find that those are 0. And then think about drawing the y-x, or the xy plane, I should say. And then finding the moments about, because that means I'm looking down the z-axis. Whichever way works for you is fine with me. I have no preference. 3D moments are a bit complex. Find a way that works for you. If you can work both of them, go for it. Pick your preference. Which one do you like more? That's a good stopping place. I'm going to stop this one here and upload this video.